Assalamualaikum and good day to Dr. Ana Sakura and Dr. Abang Muhammad Nizam. Today our group UJ Incorporation will briefly present about the group project that was conducted throughout this semester. The background of this project, which then leads to IDP, is to propose a material handling system to transport 70 litres of Nipasep across the river from Kampung Lubuk Kura to Pusat Pemprosesan Apong. This is due to high demand for the Nipaseps as it is healthier and can be used to replace the commercial table sugar. To experiment and test our design and concept, we created a scaled down prototype of a system to transport 7 litres of liquids from point A to point B, which is the boat race. We will explore various factors that must be considered when designing and operating a system for the transportation of liquids. This will include the type of properties of the liquid being transported, the limitations of size and shape, the materials used in the system construction, and the environmental conditions in which the system will be operating. We will also consider the potential risks and hazards associated with the transport of liquids by the system, and how this can be mitigated through the use of the appropriate safety measures. Through this project, the knowledge about designing concept and processes, for example like TRIS, HOQ which is House of Quality, PDS, Product Design Specifications, PU chart, FBD, and calculation using the summation of forces to calculate the forces present will help in constructing the prototype. Through extensive research and testing, we plan to develop a material handling system design that utilizes recyclable materials and construction techniques to create a system that is both sustainable and prioritize safety.
So today I will be discussing about the problem statement. So our problem statement is to create a prototype of boat that can transport 7 liters of water from point A to point B without spilling any water during the journey in the safest and quickest way. The prototype must be able to navigate through different water conditions such as rough wave or calm water, which depend on the environmental factors. Furthermore, it must be able to support the weight of water without tipping or capsizing. And lastly, the prototype must be able to demonstrate its ability to transport the water safely and effectively across the pond. Moving on to the objective, firstly, we have to design a safe material handling system (MHS) that can transport 7 liters of water. Secondly, move 7 liters of water from point A to point B. And lastly, demonstrate the safety features of the prototype for water transport.
Now, we should start by generating the concept of our materials handling system. But before that, we will be required to gather some information regarding the site where the material handling system will be installed or used. So here are some of the information that we have gathered regarding the site.
Firstly, we have the distance. It is approximately 8 kilometers from Kampung Lubuk Kura to the jetty, which is near to the Pusat Pemprosesan Apong. Secondly, we have current and tide, which is changed frequently. And the available facilities are jetty and solar system light. For debris, we have twigs, leaves, and rubbish, which are floating around the river.
So here I would like to explain the concept generation, specifically in PU chart. So basically PU chart is a method that we use in order to determine the optimal choices by comparing a few concepts. So our group have come out in the discussion with 5 different concepts in order to transport the 70 liters of Nipasep. The first one is the boat, and the second one is the drone, the third one is the pulley system, the fourth one is the bridge, and the last one the underground piping system. Based on our discussion, we have decided to choose boat as our transportation method to transport the 70 liters of Nipasep. We have a few criteria in order to choose the reason why we choose boat based on a few criteria. For example, based on the accessibility, the speed, the safety, the durability, and the price. Let's take a very simple example. If you look at the price, it is cheaper for us to buy a boat or to build a boat compared to if we need to build the underground piping system or if we compare to the bridge, we need to build it, and I think it takes more time, and the transportation will be depends on the system, so it will be it will take more time for that. So the boat are considered as the best choices here.
So moving on to the trees diagram, based on our analysis of the design of our boat, we have obtained 5 important principles, which is segmentation, chip shot living object, dynamics, beforehand cushioning, and anti-weight. So for the first principle, which is segmentation, we have discovered that by dividing our boat into several parts, such as the hull, propeller, motor, and fins, through the process of segmentation, it can improve the ease of manufacturing while preserving the strength of boat. So moving on to the chip shot living objects, materials such as polystyrene, which are low in weight and density, but at the same time, it is strong and durable, and it can be used to optimize the boat's material. Thus, this will improve the boat's strength and reduce its weight while being cost effective. We apply the principle of dynamics as suggested by the contradiction of number 9 and 12, and this improve the flow of fluids around the boat as it moves through the water. For beforehand cushioning, it helps to improve the repairability of our boat. By using Lego, components such as motors, shaft, gears, and brakes can make it easier to assemble and disassemble the boat. And lastly, we have anti-weight. To offset the weight of the load, we use recycled plastic bottles to increase the buoyancy of the boat and enable it to safely transport up to 7 liters of water. Then this will ensure that the boat is stable and able to withstand the load without capsizing the boat.
Moving on to the configuration design. Configuration design is the process of establishing the general shape, geometry, and the materials of the components. So there are 3 types of components, which are 1. Standard parts, which comprise of the polystyrene, container, Lego bricks or plates, Lego Technic shafts, Lego gears, and the bottles. Number 2, special purpose parts. This includes the electrical box, fins, bottle holder, and turning propeller. As you can see, it is only the 3D printed components that are specialized to cater for our specific boat design. Lastly is standard assembly, which are the Lego Technic motors, remote control motors, and the batteries needed to power the system. For materials, we chose most of the materials that are rust resistant. This is because the boat in the real application will be partially submerged into salt water, which promotes rust to happen. Therefore, polystyrene, plastics, rubber, and PLA are all rust resistant. The materials used are also strong to withstand high currents and forces, with low density to ensure the safety of the boat, which is it will float. We opted to use a steamship pedal design as our propulsion method, since it is easier to implement using Lego bricks and plates, and due to the limitations of Lego pieces that we have. We also implemented a remote controlled motor at the front of the boat for maneuverability, which enhances the safety of the boat. Lastly is the shape of the boat, which is made to be as streamlined as we possibly can make it to reduce drag forces acted upon the boat. Now, parametric design. This process is where quantitative measures are put into place to calculate, measure, and figure out the forces acted upon the boat and the forces that are required to make sure the boat will float. This process also touches on the exact dimensions of the boat, which will be displayed during the detailed design phase for the presentation. For now, here is the orthogonal drawing of the whole boat. Moving on to the calculations first, since we are required to transport 7 liters of water in the prototype, we will require the same amount of upwards or buoyant force to ensure that the boat will float. Since we will be using 500 ml bottles for our flotation system, we have calculated that we need at least 14 bottles to ensure that the boat will float safely.
Product architecture can be defined as 3 things, namely the arrangement of functional elements, the mapping towards the physical components, as well as the specification of the integrating module. Now there are 2 types of design architecture, modular and integral, and in this case we are using modular. So from there we can draw the schematic diagram. The boat schematic diagram, as you can see, the red box represents the physical chunks. There are 4 chunks there, namely the storage module, the power generation module, the buoyancy module, as well as the control module. The functional elements are in the blue box and its function is in the green box. After the boat schematic is done, we can construct the rough geometric layout for the material handling system, which shows the overall placement of the functional components in the designated area. So the goal is to get from JTA to JTB, and we plan to use a boat. Detail design is a phase where all the details of the boat are brought together and the decision on the boat has been finalized. So as you can see, this is the orthogonal drawing of the boat. So here are more orthogonal drawings of the functional components of the boat. So the one displayed here is the box, the fin, the bottle, as well as the hull of the boat. Here are more octagonal drawings of the functional components. So there is a container to transport the 70 liters of Nipasep. There is also a bottle holder to make sure that the bottle is in place. There is a turning propeller as well as the propeller body to put the turning propeller together.
So that is all from our group. Thank you very much.